Hello and welcome to a short introduction video about IP networks for audio visual engineers. This is based upon the last few months of work with various AV contractors and systems integrators, and there are some common themes emerging across the industry. So the first thing everybody says to me is we want simple networks for AV, and that's absolutely fine because most of our work in AV is to create simple and good user experiences. So we'll look at a safe and simple IP addressing scheme that we could use. This works very well for most AV services. We'll have a quick brief touch on different vendor specific IP control implementations. We'll have a brief touch on IP interoperability standard support from vendors. We're going to look at that briefly because there's a huge amount of detail and conflicting information on this, and I don't think anybody can be across up to the minute what messaging is coming out in the sector at the moment. So what we're going to focus on is we're going to look at a real and safer integration of our IT infrastructure, and we'll look at a simple normal context in the kind of networks that we're going to see in day to day. Now, this is not pretending this is definitive. There is no such thing. There are massive networks out there where close integration of IT services is absolutely essential. If you want to look at this information, that's fantastic. But if you're dealing with such a network, that's a very, very specialized activity, and there are lots of contextual considerations to go into, which is more of a consultation, long-term engagement. So as a result of that, we're not going to discuss complex IP rooted infrastructures. We're not going to look at global scalable approaches, and we're not going to go in any deep dives into specific technologies here. So we're going to look at a safe and simple IP address scheme. The first thing we need to look at, let's get a plan together of how we're going to plug everything in and look at how we address things. I'm going to keep it to a very simple integration because this scales up and there are many, many options available. So the key thing to remember is most services in AV don't need an internet connection. There are some that may need that, but in most of the time, when you look at smaller offices or live audio, the bridging point to the internet connection may be just a telephone conference system or something like Teams, and which is normally and well understood now, especially since the lockdown. That's well understood by corporate IT departments. What we're looking at are the kind of networks that you may be deploying on your own or as part of an IT integration. So the thing to remember is most deployments in AV can fit within an address scope of 254 devices per service. So most deployments don't really require IP routing in most, and I'm talking about most being the majority of cases. Inevitably people are going to say, well, I've got a project that needed IP routing. Yeah, they exist. Of course they do. We're not talking about this specifically today. Therefore, we don't need to worry about gateways and internet routing if we're not doing IP routing. We don't need to worry about variable length subnet masks, classless interdomain routing, and most parts of a formal network engineering course, and also as a result, routing protocols, load balancing, network security appliances, and such. That's not the focus of this particular presentation. So what we might consider how we can use VLANs to segment the different kinds of traffic on our AV network. We can look at safe access to multiple services from a single point, i.e. An operator or a commissioning engineer wanting to access all the different services from a single laptop rather than have a forest of computers and computer screens and a jungle of cable to wade through. And what this does is it can make troubleshooting easier. How we can implement this so that things are transparent, easy, linear, and how to understand. And it also helps us to understand how we can assign addresses, where having different addresses matter, and where they're nice to have just for reference. So let's look at a simple example. Of course, a very, very popular PA system in the world and a fantastic one is L'Acoustics from Paris. They have a piece of software called LA Network Manager. It's a great way to manage all of your network controlled amplifiers. It recommends assigning addresses in the private IP subnet of 192.168.1.0/24. That means that gives you a decimal subnet mask of 255.255.255.0. It can deal with other address ranges as well, but we'll look at this recommended default. Now, the actual control software is not IP routable itself. It does allow for IP routing if, for example, your amplifier is talking to an SNMP service. That's a server that logs information and allows people to monitor this in third-party software. So if you're just controlling your amplifiers, you don't need a gateway. If you're using SNMP to monitor things estate-wide or deal with third-party controllers like Crestron, you'll be very, very well aware of whether you're using these things or not. And then how to implement a gateway is a separate topic and not the focus of this presentation, but we're happy to talk about that as well. So in this configuration, it's possible to manage 253 amplifiers. It can work with third-party software, like I said. Sending data service such as SNMP and third-party controllers may benefit from routing. We're not addressing this here. So most setups will have fewer than 253 amplifiers. That's a lot of amplifiers. Very few setups will need to work with third-party devices in a different IP subnet, and it's therefore proposed we follow the default examples. This will become clearer later, but we're just taking this, that I'm declaring the assumptions we're making. Now, of course, if these assumptions are at variance with your particular implementation, of course, that can be accommodated, but we're trying to keep things simple and headline to using a generalization to make a specific point. So another simple example, Sennheiser. Sennheiser WSM can work in an IP routed network. This means that it can control devices in multiple subnets if the routing is set up and the gateways are set up. This is mainly because WSM is designed to work across enterprise as well as in a live scenario, so having that flexibility to allow control information to pass across a corporate routed network can be of benefit. So we're going to look in this discussion, aiming for simplicity, we're going to look at smaller setups. We're assuming we don't have more than 200 Sennheiser devices. It would be nice, but let's assume we don't for the moment, and that they're all physically located close to each other. So that means that we can deal with one IP subnet in this. So as we saw, the documentation of L-acoustics is clearly expressed. In the solution we're discussing, we could use the same IP address range, 192.168.1.0/24. We could actually use that in the example we're going to look at. We can use the same address range for the Sennheiser devices. You might not want to do that because just in case there's an external route, I'm going to look at methods for avoiding this. But also, sometimes it's nice to just be able to look up numerically and understand what service a device is. If you remove that granularity by having a single numbering system, it may or may not be of benefit. I don't have a strong opinion either way. It really depends on context. So if people are scratching their heads saying, you've got duplicate IP addresses, are you mad? Well, it'll become clear why I'm not, but I perfectly understand why you would not want to implement that in reality. That's perfectly all right. So we can clarify this maybe. So no, it's not bad to use the same IP address in this context. In a lot of other contexts, yes, it's very, very bad. What we're doing, like I said, we're making an assumption that each service has a small enough number of participating devices that we can occupy a single/24 subnet. We also assume that the Sennheiser devices have nothing of interest to L-acoustics devices. We're not assuming that the humans are disinterested. Obviously, a systems tech may want to control the amplifiers and then may have some responsibility for managing radio mics or mixing consoles, of course. But computers are computers and humans are humans. So mistake number one we often find with people working with computers is some kind of anthropomorphism being engaged where computers are imbued with conspirational powers. Obviously, most of the time I can get very, very frustrated with the computer. I tend to think it's myself that's doing it wrong because computers are basically dumb, inanimate objects, and hey, they don't listen if you scream at them anyway. So how can we get away with this behavior? Well, in short, what I've just proposed is we're building a separate network for, in this case, the L-acoustics amplifiers with their own switch, with their own laptop controller, and some Sennheiser radio mic receivers, again with a different switch with a different laptop. Now, of course, because there's nothing in common between these two things, we could, of course, use the same IP address for amplifier number one as radio mic receiver number one, because they are essentially, on different planets to each other. This is where I'm beginning to build it up from the ground. So we're looking at this as the first principle thought. The hypothesis being, if I had separate switches and separate cabling and separate control computers, I could use the same IP address over and over again. Now, of course, we all know that the internet and modern networking doesn't necessarily force us to do this, because it's quite expensive because we have duplicate cables, we have duplicate switches, and we also have duplicate compute. So we're going to look at the safe way to combine these things, get the money saving benefits and the less cable jumble benefits, but also maintain this first principle idea so we can deploy things safely and actually, more importantly, troubleshoot things rapidly when something may go awry. So what we don't want to do, we don't want to have accidental IP routing. We want to maintain separation between services. We need to avoid allowing an active full stack device that we don't finally control making things up. Now, what I mean by that is a desktop operating system. Desktop operating systems are the things that run on probably the computer you're watching this on now. It's there to essentially connect to the public internet and browse web pages. Maybe you're watching this on YouTube, and it's not an IP router. That's a separate box traditionally, which has concerns of IP routing. Now, it may be software based inside the box, but it will have a different setup and a different operating system set of preferences to your desktop operating system. So a desktop, and by extrapolation, a laptop operating system, has complex what we call binding rules. This is how does an IP address map to a particular network interface. So one thing to be really careful of is having a forest of different network adapters attached to one desktop operating system, and that includes laptops, each with different IP addresses. You can even assign VLANs on some of these adapters, and hoping that the traffic will stay separate, because of course the second you've assigned it an IP address, in most operating systems it will start to engage in IP routing, and the operating system may or may not start routing that traffic between your different subnets that you want to keep separate. Now, the other consideration here is it will also have an idea of a default gateway, and that can get corrupted because depending upon the power up order, that isn't always strictly bound. Think about carrying a laptop around. You may have a laptop, it's plugged into a wire on the desk, as mine is at the moment. If I unplug my internet cable, as it were, it will go looking through the wireless access point, and it will get a route to the internet through the wireless access point, and it may get a different IP address because that may be on a different network segment, and life with the internet will resume in short order. That's not the kind of thing that we want in an AV network, because we want to have a good idea of what our specific signal path is at every moment of the day. Otherwise, things get confusing. Imagine this: if a power up sequence changed the default gateway and the binding on that in your operating system, it would be incredibly difficult to troubleshoot. Believe me, I've been there and I've been scratching my head. And until I learnt about all kinds of complex tricks I can do with desktop operating systems, it's just miserable. So what I'm focusing on here is how to avoid having to think about these things and get on with the primary purpose of being in AV, to make good sounds and have a good user experience. So where can we start? We could use port-based VLANs to separate the endpoint devices. Many people there are aware of VLANs, so we can assign on this the 3 ports where the amplifiers are plugged into the switch. We could assign them to VLAN A. We could assign the 3 radio mic receivers to VLAN B. I'm deliberately not using numbers because VLANs have numbered tags, so let's call it A and B here, even though in a real implementation they will have a specific number. Then we could potentially send all of the traffic together up the same cable using what we call an 802.1q trunk port, and that means that we can send Ethernet frames up that cable, and they maintain their tag, so A for the amplifiers, B for the radio mic receivers. They travel up there together, and we hope we hit another trunk port and they get separated out further up. This is one of the nice ideas. People were building trunk ports onto their desktop operating systems, assigning VLANs to them, and then letting it all escape into their desktop operating system. It correctly identifies there's different IP subnets here, and of course IP subnets, that means we're going to do routing, because that's what IP subnets are for, aren't they? They're for routing between. So the laptop gets involved, and as soon as you look at it, it starts routing traffic between subnets, which is a common thing for desktop operating systems to do. So that's why I can't emphasize strongly enough why we want to avoid that scenario. Obviously, the other side of things, that the temptation is quite a happy temptation, is we want multiple users to see the same control computer. One of the motivations of having this all delivered to a single desktop is, well, that means I can access network services for, say, amplifiers and, say, for radio mics. We could access them on the same computer screen, so we don't end up with this massive forest of screens and tons and tons and tons of wasted duplicate computers. So we're going to discuss a method we can use to make this safer and also allow for more people to access it actually in the end. So how we can stay safe? Well, we can use this trunk cable that I talked about, but instead of connecting it to a desktop operating system, let's connect it to a virtual server. And then inside that virtual server, we can run a virtual machine for each service. People may be familiar with desktop operating systems that support virtual machines. We'll more on that later. So inside our virtual server, we could have 3 Windows virtual machines in this case in the illustration. So I connect VLAN A from our virtual switch up to my first virtual machine. So that may run my L-Acoustics network manager software. Virtual machine B is just a spare one. It's not doing anything at the moment. And machine C, that could be running WSM from Sennheiser, and that can happily just do that. And virtual machine A is just doing the amplifier management, which is fantastic. So the software we use to let us do this is called a hypervisor. Now there are many hypervisors available. They're commercially supported, or there's open source ones even as well. And this allows remote desktop access to the machine that is being hosted. So we call these virtual machines, we say they're hosted within the hypervisor. A user could access more than one virtual machine from a laptop. If you have access to the hypervisor, there'll be a terminal screen that gives you a remote desktop, and you can just pop those open in different windows. You could have multiple machines open at the same time if you have enough screen real estate. I often have 4 or 5 machines open on remote desktops on my machine. I'm running a estate of probably 20 or 30 virtual machines in my hypervisor cluster, and that's just how I manage things day in, day out. It actually becomes much more compact. It feels like a lot of extra heavy lifting in a Turing system until you start actually getting busy, and then as it scales up, as you get more familiar with it and use it more, the actual heavy lifting on this becomes less. So I'm making the assumption here, at no point would the L-Acoustic software be interested in what the Sennheiser software is doing, and certainly an amplifier wouldn't necessarily be interested in what the control side of the RF side is doing. I want amplifier control. I want to control amplifiers on that machine. I want to control my frequency management and what the health of my radio network is on my other dedicated radio machine. Now, of course, this brings up the interesting case of when we might want to have some kind of audio interoperability between mixing consoles, for example, radio microphones, that also connecting to our amplifiers as well. So then we start to look at the scenario of, well, how do we connect this together? And that's also one of the reasons why there is still this popular thing to connect to a control network, quote unquote, and a separate audio network with separate physical connectors. It's understandable. If you want to avoid doing IP routing, it's actually probably quite a pragmatic approach and quite a good way around it. Of course, if you want to merge all of these things together and have the panacea of an IP routed network and build something of that complexity, then you may still be using hypervisors. You would be using switches and routers. It's a much more complex network setup, and it's outside the scope of what we're talking about today. But absolutely happy to advise on those, but that is really on a specific context basis. So what about VirtualBox? I did mention it in passing earlier. VirtualBox is a piece of software that you can download from Oracle. It can run on Windows, it can run on Mac, it can run virtual machines. Personally, and this is my own ignorance and stupidity, I find managing the network stack and keeping the separation strong on VirtualBox something I would not wish on my worst enemy, to be honest. I've got used to using hardware-based virtual server hypervisors, and that works much more like the hardware for me, and there's a lot more power when it's deployed inside a server. So yeah, it might work on VirtualBox. I'm definitely not an expert on this kind of thing. There's also VMware Player, which is free for one instance. I prefer how it manages networks to VirtualBox, but that is personal preference. But for me, I always use a server-based hypervisor, and that just gives me the power and flexibility. So it seems complex. It does undeniably introduce some complexity. It does simplify things when unpredictable behavior happens on the desktop OS. So should your desktop OS get randomly involved in doing some IP routing that you didn't want it to do, and troubleshooting that, and it will always happen at the worst moment. It will always happen before the CEO walks onto the stage in a corporate environment, or probably somewhere into the third song of the headline act in a live environment. Everyone knows that, everyone's been there. And when computers start behaving randomly and irritatingly, they will always pick the worst time to do it. It's Murphy's Law. So at least adding this complexity here is it's a known addition of complexity. We can actually quantify what we've done with the complexity, as opposed to our unknown, non-quantifiable complexity, which is the worst enemy of any kind of troubleshooting process. And that's something could happen, a cable could get unplugged, something could change in our environment, and the desktop operating system makes a bunch of decisions which only it's really privy to. So in summary, we could use a /24 class C style subnet, which means we're using a private IP address range. If we use a /24, so 255.255.255, that gives us the potential for 254 subnets in class C of 254 devices each. Each of those devices can be uniquely addressed. So for example, 192.168.10/24 for the acoustics network we've proposed, 192.168.3.0/24 for the Sennheiser network we're looking at. We can allow an unused subnet for users to connect to the hypervisor. It has an outside-facing network interface, and that's where we would typically allow our operators to connect to the hypervisor, set up access privileges, and allow them to use the virtual desktop to view what's going on, and maybe open multiple virtual desktops so they can look at multiple machines at once. This also gives us the nice thing where if we have a better resilience because we're not hanging it all on one desktop operating system. Should, for example, one Windows machine crash, the other ones will keep going because they're completely unrelated to the one that may have crashed. We can just restart that machine. We've only lost one service and we can carry on with everything else and wait till that recovers and do a different job. If we really are hell-bent on doing IP routing between different subnets, we can achieve that. We could install a virtual router within our hypervisor network. This is how my home network's implemented. I have a software-based router. It's very, very powerful. I can manage multiple subnets. It can do routing between different subnets, and we can turn that off. In fact, on most software routers I've used, it's off by default, and then you have to specifically enable it by allowing firewall rules to allow traffic in and out. This also could allow access to remote desktop protocol on the Windows machines you're running inside. So someone could just log in direct to that remote desktop session rather than going through the hypervisor interface. There's lots and lots of choices that could be made in terms of what your security sensitivities are. So this was a short concept flyby of something that might be done to protect against inexplicable random behaviors and how this can help. So AV and IT Technical are happy to advise on specific implementations and designs. We're more than happy if you want to get in touch. You can email me, kieran.walsh@avinitTechnical.com. And thank you very much for your time. And I would be really, really interested to correspond with people offline. And if anybody's got any questions about this material, please feel free to drop me an email.